So we're going to do some guided practice for basic torque problems. You should have this page out. We're going to do the first few together and then you can work on the rest on your own. So how much torque is produced by a 400 Newton girl sitting on the right side of a seesaw 2 meters from the fulcrum? So I always first draw this out. I'm going to put the fulcrum here and we have this girl over here and her weight, her FG, is 400 newtons, and we know that the distance is 2 meters from the fulcrum. So that's the information that you have. So to find the torque, torque is force times the distance of the lever arm times sine of the angle, and the force is 400. The distance, the lever arm distance is 2, and the angle is 90. It acts at an angle of 90 degrees. So this is just 800. That's pretty simple. The units are newtons times meters. There's no shorthand for that. Okay. So number 2. How much torque is produced by a person pushing clockwise with 2 newtons on a faucet 0.060 meters from the pivot? So here's our faucet. So we'll imagine that it looks like this, right? And it's got, this is what a faucet sort of looks like. So if you're pushing, if you put your finger, one finger is here and usually your thumb is on the other one and you go to turn, so you're putting a force. So we're going to say that you can push with 2 newtons, right? That's your force. And this distance from the faucet is 0.060 meters. So the torque produced is force times distance times sine of the angle. Again, it's going to be 2 newtons times 0.06 meters, and the angle is 90 degrees. See right here, that's 90. So you get 0.12 Newton meters. Now because they said clockwise, you would call that negative because this is, right, that's your clockwise direction is always negative. I totally drew this going the wrong way. It should be going this way, right? That's the clockwise direction. We didn't talk about the sign up here. Here we're going counterclockwise, so this would be a positive. So number 3, how far from the fulcrum should a 0.2 Newton toy be hung to create a counterclockwise torque of 0.3 Newton meters on a mobile? So you're given the torque, and this is your counterclockwise torque, so that'll be a positive number. And you know that the force of gravity acting on this toy is 0.2 newtons, and you want to know this distance, right, which is your lever arm distance. So torque is force times distance times sine of the angle. So 0.3 is 0.20 times r, and you're going to assume that that's 90 degrees, right? You're hanging, well, a mobile, right, looks like this, and if there's something hanging here, that's at 90 degrees. So that's where that's coming from. So 0.3 divided by 0.2 is 1.5 meters. That's kind of a really big mobile to hang in a baby's crib. So what you want to do next is you want to do the other examples using the same general techniques. They're pretty straightforward for 4, 5, and 6. Number 7, 8, and 9 is an interesting problem. I'm having to do more conceptual with the diagram. So give that a try, and then you can come back and check your answers when you're done. Here are the answers to 4, 5, and 6. Hopefully you've done this. This is pretty straightforward. They give you these values to plug in, and you get 120 for Sherry, 137 for Jose, and the door will rotate towards Jose because his torque is greater, so that there's an imbalance in his direction. 7 through 9 is a very interesting problem because there is a shape, right, with all sorts of lines, forces shown. And the only ones that will exert a torque are the ones that don't act along the axis of rotation. So if you have to, in order to figure it out, what you do is you have to draw a line from the perpendicular to your of the line of action back to the center of mass, and you can see if there's any distance there. So FA, FH, and I think there was one other. Oh no, those two run through the center of mass, so they're not going to exert a torque. They can only make it move linearly, translate. But anything acting at an angle will exert a torque. So the torques that are, how we figure out how big they are is you draw, we have these lines of action, and perpendicular to that, let me do that in a different color, right, would be here. This is perpendicular. So this is now what we call the lever arm. So let's do that for another one. So if you take this one and draw, right, you have the line of action on your paper. Mine is not really to scale. But if you draw perpendicular to that to the center of mass, right, there's your perpendicular, that lever arm is bigger. Now this here is the lever arm for G. That's bigger than FB's, but let's see if we can find one that's bigger. So you keep doing this until you find the one that's biggest. So here's your line of action, goes this way, and your perpendicular distance is right here. So this is for FD. The biggest one you should find is for FE, because the perpendicular to that is all the way out here, right? So this ends up being the biggest lever arm. That's why, right, this perpendicular, I didn't draw it so great, but this is the perpendicular to the center of mass. That gives you your lever arm. That one's the biggest. It's bigger than FC. It's bigger than FD for sure, bigger than FF.